Today, we will focus on the inner solar system. The four planets of the inner solar system, Mercury, Venus, Earth, and Mars, are considered terrestrial planets, or Earth-like. They're all rocky. They're composed of large amounts of rock and iron. And by rock, we mean primarily silicates, which have a lot of silicon and oxygen, as well as trace amounts of other metals like aluminum, magnesium, and so forth. The terrestrial planets are not massive enough to keep hydrogen and helium in their atmospheres, but they are able to keep the heavier elements. So as a result, their average density is higher than gas planets. Density is represented by the Greek letter rho, and it equals a mass per unit volume. So mass over volume. Now, for a planet, the volume is approximately a sphere. So since the equation for a sphere, the volume of a sphere, is 4/3 times pi times the radius cubed, we can substitute this in to volume in our density equation so that we can find the density of a planet just from its mass and radius. It would be the mass over 4/3 pi r cubed. We can measure the mass of a planet if we can observe something that's orbiting that planet. We can measure the radius of a planet by its angular size from our point of view, as long as we know how far away it is from us. In the absence of geologically active surfaces, we can often observe lots of craters on some of these bodies. By counting the number of craters per unit surface area, we can estimate how old that surface is. If it has more craters, then it's been around for a longer time. Before we look at each of these four terrestrial planets of the inner solar system, we can ask, are we sure these are the only four? Urbain Le Verrier, the same French mathematician who helped calculate where Neptune should be, proposed that there might be a planet in between Mercury and the Sun. He thought this due to some peculiarities with Mercury's orbit. This hypothetical planet was called Vulcan. Many searches have been made for Vulcan, but no planet has ever been confirmed. If there are any volcanoids, or any objects in between Mercury and the Sun, they are probably smaller than 5.7 kilometers in diameter. Mercury is the first planet from the Sun. It is called Mercury after the messenger of the gods, because it orbits the Sun the fastest. It only takes Mercury 88 Earth days to orbit the Sun, but it also takes Mercury about 54.65 Earth days to spin on its axis in relation to the distant stars. That's 2/3 of its orbital period. And Mercury is locked in this 3-2 spin-orbit resonance. An observer on Mercury would see only one Mercurian day for every 2 Mercurian years. Mercury has a more eccentric orbit than the other planets in our solar system, and the spot in its orbit where it is closest to the Sun, called perihelion, precesses around the Sun, but it does that at a different rate than what is expected by Newtonian physics. This is the main peculiarity of Mercury's orbit that Urbain Le Verrier was concerned about. It turns out that the precession of Mercury's perihelion is explained with general relativity. Mercury has little to no atmosphere, and that means that it has extreme temperature variations. On its equator, it can be 100 Kelvin at night and then 800 Kelvin during the day. At the poles, it's constantly below 180 Kelvin. There have been only a few missions to Mercury, with Mariner 10, which flew by in 1974 and 1975. Then the Messenger orbiter, which launched in 2004 and orbited Mercury through 2015. The Bepi-Colombo mission from the European Space Agency is on its way to Mercury now and should arrive in orbit in 2025. Venus is the next planet from the Sun. Venus has a slow backward spin. It orbits the Sun in about 224 Earth days, but it takes 243 Earth days for Venus to spin once, and its spin is backwards compared to the direction of its orbit. Venus has a thick atmosphere, and it traps in the heat from the Sun. So as a result, it's a lot hotter than Mercury. Its atmosphere is mostly carbon dioxide, and it has clouds of sulfuric acid. Venus has experienced what we call a runaway greenhouse effect. Its atmosphere blocks the thermal radiation that's coming from inside of it and prevents it from escaping into space. So it becomes even hotter. And when it's even hotter, it makes it even harder for that thermal radiation to escape. And that makes it harder and harder for this to be reversed. The Mariner 2 mission flew by Venus in 1962. The Soviet Venera 7 landed on Venus in 1970. And in 1991, Venus received an orbiter, Magellan, which was able to use radar and make maps of Venus. We've talked about Earth before, but instead of skipping over it, let's pause for a second to understand it in this context as the third planet from the Sun. Earth stands out because it has a surface hydrological cycle. Water rains down from the clouds, it evaporates, and then it condenses again in the atmosphere. No other planet in our solar system has water on its surface. Earth has a magnetic field that is generated by liquid iron spinning in its outer core. And Earth has a convecting mantle that drives plate tectonics, helping to renew its surface. Mars is the fourth planet from the Sun. The Martian year is slightly shorter than 2 Earth years, and the Martian day is just a little bit longer than an Earth day, about 24 hours and 45 minutes. Mars has 2 moons, Deimos and Phobos, but they're both small. Mars has a thin atmosphere with occasional dust storms. Mars has ice caps at its poles that can be seen from Earth. Mars has a strange hemisphere dichotomy. Its southern hemisphere is a few kilometers higher in altitude than its northern hemisphere. This results in some differences between the northern and southern polar ice caps. Because the acceleration due to gravity is lower on Mars, Mars has more extreme mountains and valleys. The tallest mountain in the solar system, Olympus Mons, is on Mars, as well as one of the deepest canyons, Valles Marineris. Mars has received many missions. In 1965, Mariner 4 flew by. In 1971, the Soviet Mars 3 landed, but it lost communication just a few seconds later. In 1976, Viking 1 made the first successful landing on Mars. In 1997, Mars Pathfinder arrived with the first rover, Sojourner. In 2003, the European Space Agency's Mars Express orbiter arrived. The next year, 2004, NASA's Mars exploration rovers, Spirit and Opportunity, were deployed. Spirit operated until 2010, and Opportunity operated until 2018. The Curiosity rover arrived in 2012. In 2014, India's Mars orbiter mission arrived. A new rover is now being sent to Mars, Perseverance. After the 4 terrestrial planets, but before we get to the outer solar system, we have an asteroid belt. Now, there are asteroids between all the inner planets too, but the main asteroid belt is between Mars and Jupiter. Jupiter is preventing these asteroids from accreting into a planet. Jupiter also carves out what are called the Kirkwood gaps, specific semi-major axes in orbit around the Sun where there are fewer asteroids due to resonances with Jupiter's orbit. Ceres is the only gravitationally rounded object in the asteroid belt, so as a result, it became classified as a dwarf planet in 2006. Ceres has a transient atmosphere called an exosphere. It is quite a bit smaller than our moon. Listed down here are the four largest asteroids: Ceres, Vesta, Pallas, and Hygeia, along with their mean diameters. The combined mass of these four largest asteroids accounts for half of the mass of the asteroid belt, but that is still only about 4% the mass of the moon. NASA's Dawn mission went into orbit around Vesta in 2011 2012, and then it went over to Ceres and started orbiting Ceres in 2015. The mission ended in 2018 when it had exhausted all its fuel, but Dawn is still in an uncontrolled orbit around Ceres. There are different ways to classify asteroids. One of them is due to their position. We have the main asteroid belt in between Mars and Jupiter. There are also the Trojan asteroids, which are in Jupiter's orbit. Some of the Trojans are near the stable point ahead of Jupiter in its orbit, and some of these Trojan asteroids are near a stable point behind Jupiter in its orbit. There are also these Hilda asteroids in a resonance with Jupiter. And there are also a lot of near-Earth asteroids, many of which are classified as potentially hazardous asteroids. Another way to classify asteroids is by their composition. The main types are C, S, and M. C stands for chondrite. These are common asteroids consisting of clay and silicate rocks. S-type are stony or silicate materials, and also nickel and iron. M-type asteroids are metallic, mostly nickel and iron. The differences in composition are most likely due to where they originated. The most advanced telescopes today are used for research, and these are placed in the best locations, either summits, such as Mauna Kea in Hawaii, or in the mountains in Chile, or in space, where there's no atmosphere to obstruct their view. The Hubble Space Telescope is the most famous of these space observatories, but there have also been Spitzer Space Telescope, Kepler Space Telescope, looking for exoplanets, succeeded now by TESS, and we hope soon that the James Webb Space Telescope will succeed the Hubble Space Telescope. When you think of a telescope, you probably think of looking through a telescope, but a lot of these research telescopes will take pictures or record videos of what they are observing, and they do not have to observe in the visible part of the spectrum. In fact, much astronomy today is done outside the visible part of the spectrum. Radio telescopes are an example of that. They observe light that's in the radio part of the electromagnetic spectrum. An advantage of radio astronomy is that our atmosphere does not block radio wavelengths. It isn't difficult today to get your own telescope. Through your backyard telescope, however, do not expect what you see to look like images that the Hubble Space Telescope has taken. At night, our eyes are less able to see color and are adapted better to see motion. So when you do look at nebulae and galaxies, they'll be dim and they will also be grayish. If you want to go into astrophotography, your camera may capture a lot more color than what your eye could. And also, with astrophotography, you can set a longer exposure time to allow your telescope to collect more light. Collecting light is actually an extremely important part of observing with the telescope. and that is done through having a larger primary aperture. A larger primary aperture also helps to have a greater angular resolution, so you can see more details. The main purpose for getting backyard telescopes would be for wonder and awe, looking out at the stars, also for educational purposes. But it still is possible to do research with backyard telescopes. Certain astronomical events, such as transits and occultations, as well as supernovae, are all transient phenomena. Whoever is in the right place at the right time can capture these. And a lot of amateur astronomers have contributed to science in these ways. There are two main types of mount for a telescope: an equatorial mount and an altazimuth mount. The main advantage of an equatorial mount is that you can use coordinates like right ascension and declination to find a specific celestial coordinate. And it's easier for an equatorial mount to have a clock drive that will rotate to counteract the rotation of the Earth. The advantage of an altazimuth mount, and one type of this is the Dobsonian mount, is that it is more intuitive to move around and find objects. I would recommend the altazimuth mount for your first telescope so that you can more easily explore the night sky. Also, while you do want a larger primary aperture to collect more light, that would also result in a heavier telescope. So the best telescope is one that is still light and small enough that you actually use often. Telescopes from the ground are not enough to explore space. We also want to leave the Earth's surface, and for that we need rockets. Recall Newton's laws. By Newton's third law, action and reaction, rockets propel themselves forward by pushing exhaust out the back. That way, even in space, they can accelerate. But they do need to use most of their fuel just getting out of the Earth's atmosphere. By Newton's second law, a greater force is required to accelerate a greater mass. So rockets are often multi-stage. Some stages will just contain fuel, and when a rocket has used all the fuel from that stage, it can detach that and thus decrease its mass. Once a rocket has reached orbit, it doesn't need to expel exhaust. It would only use its fuel when it needs to make corrections to its orbit. For a circular orbit, an object needs a velocity equal to the square root of g, the universal gravitational constant, times the mass of the object it is orbiting over the radius of that orbit. For an object to reach escape velocity, it needs a velocity of 2 times gm over r. So that from orbit to escape, it's only a factor of the square root of 2 of an additional thrust. If an object doesn't have enough velocity required for the orbit, it will fall to the ground. We have launched a lot of satellites into orbit around the Earth, and there are diverse purposes for doing so. Astronomy, such as the Hubble Space Telescope, looking outward. There's also satellites for Earth observation, looking inward. There are a lot of satellites for communication, also for navigation, or GPS. There are satellites for reconnaissance, also for weather, and there's the International Space Station. There are different types of orbits that these satellites are on. Most satellites are on low Earth orbit, but for low Earth orbit, they need to orbit faster. Recall Kepler's laws. Communication satellites especially are on a geosynchronous orbit, where they orbit the Earth in the exact time it takes for the Earth to spin. So viewed from the surface of the Earth, they're not changing their location in the sky. Another special type of orbit is called the Molniya orbit. And that orbit is shown in these diagrams. It's an elliptical orbit that is able to get down close to the Earth near the poles. The Moon, our natural satellite, is also in orbit around the Earth, but at a much greater distance. Maybe one of you someday will enter into orbit around the Earth.